Alright, today I'd like to introduce a new calculus concept, and that is using integration to find volumes of different shapes. Typically at the AP Calculus level, we just look at two different kinds of solid shapes. One is called a solid of revolution, not because of like a war or something like that, but because it's created by something spinning around an axis. And another way to find volumes is also by cross sections stacked up on a base. But we'll handle that one in a separate video. Let's look at revolutions first. I think that's the simpler one to kind of visualize. So let's look at this situation over here. So we got a curve here, f of x, which in this case f of x is the square root of x. And right now we're looking at just a typical area underneath the curve, just a regular integral. Right now my a looks like it's set to be 2 and b is set to be 9. And if we want to find this area, we're basically integrate all the x's, or actually rather all the f of x's, where x starts at a and goes to b. So we'll be adding up all of these different line segments and integrating f of x dx between a and b gives us this blue area. So that's stuff we've done ages and ages and ages ago. But this time we're going to create a solid out of this particular area. So what we're going to do is we're going to spin it around the x-axis. So what does that look like? Well, it turns out I can't draw with beans, and so I'm actually doing animation on GSP. This particular sketch was written by Audrey Weeks, and it's like many years old now, but I think it's a pretty good way to visualize what's going on. So I'm going to take this blue shape and spin it around the x-axis. So here we go. Yeah, pretty nice. Keeps on spinning there. The reason why we're getting these dark circles is when I spun it, I also spun the edge here that marked the A and also the edge around the B. And I've got this X here that I can move as well. X starts at A and goes to B. And I think I'm going to stop that spinning there. So I think you can kind of see where this is heading. So we want the volume of this weird kind of bullet shape. So it's actually not quite a bullet, that the tip's been cut off there. So we just have this sort of weird shape here. So, well, how are we going to do this? Well, if you look, we've actually got a bunch of circles kind of piled on top of each other. So she has a button that kind of shows you this. So here our X is sweeping out. The X starts at A and goes to B. And every single time you take a cross section, it's going to be a circle. And the reason why it's a circle is because of this way it got created. So remember, we created this by spinning this around. So it's no surprise that every single time we take a slice which is perpendicular to the x-axis, by the way, you're going to get a circle. If you were to take a slice this way, perpendicular to the y, it's not really going to look like circles anymore. So but slicing it this way, we get circles. So it sort of makes sense that if we add up the area of all these circles, we'd obtain the volume of this shape. In fact, that is one definition of volume, is just adding up the areas, integrating the areas of all the cross sections. So now that you sort of get the idea of what this is about, we're actually going to perform it. But before I do it, let me throw one monkey wrench into the works here. So you don't necessarily have to spin around the x-axis. Or even if you do spin around the x-axis, there's nothing to say that the area that you're looking at touches the x-axis. So I'm going to take this, move it down a bit. Maybe I'll move it down a lot. Not that much. Okay, so I'm going to take this same blue shape, but spin it around this line instead of the x-axis anymore. So it's going to kind of come out into space and come back around. So I don't know if you can visualize this, but it's going to create this big hole in the middle. So I'm going to go ahead and revolve it and watch what happens. So you can see there's this big air space in the middle as this kind of comes around. You could just stick your arm through it. So now, when you take your cross sections, you don't get full circles anymore. You get what are called washers. So I'm just going to go ahead and sweep this now so you can kind of see. Well, it turns out if you add up the areas of all these washers, you get the volume of this solid right here. And the way you could find the area of a washer is essentially this big circle take away the air hole in the middle. So all right, well, let's get onto the calculus so we can actually do some computations here. All right, So it's time to put some math up all in this. So let me bring up a screenshot of the picture we saw before from Sketchpad. So this is the region which has been revolved around this line, creating this kind of solid right here, but it's got this big open hole in it. So it's a little bit hard to tell from the screenshot, but you could actually stick your arm through that like some sort of really thick bracelet. So actually, yeah, let me pull my arm out here and just kind of show you that, yeah, you can just stick your arm right through that puppy. Alright, so in order to really be able to solve this with calculus, we're going to have to understand in a little more detail exactly where this washer came from. So let's just focus on one particular washer here. So let's just look at just this one segment which created that washer. And let's kind of follow it around. So in order to keep our orientation correctly, I'm going to go ahead and highlight the endpoint in red of the top of that segment, and also highlight the bottom in blue. So as this entire yellow shape spins around this dotted line, this one segment is going to be tracing around like that. So let's go ahead and sort of follow the course of these dots. So that's that segment spinning around. So I only labeled like a few as it went around, but you can kind of imagine if this red point were to trace through the air all the way around, it would create an entire red circle. And this blue dot here, as this black segment traced around, it would also create a circle. So there's that blue circle created by that blue dot. Now, the actual black rim right here, so I just kind of highlight in black, but really if you look at this area, it was sort of this yellowish green. So if this sort of black / yellowish green segment were to wrap all the way around like that, it would create that washer area. So if we want to compute what the area of this washer is, let's look at it head on. So it looks like these are ellipses, but that's just the perspective of this drawing. If we actually looked at it head on, it would look more like this. Okay, so this blue circle right here was created by that blue dot, that blue endpoint as it wrapped around. This red circle over here was created by this red point as it rotated around. And this little black segment here, that's our little X slice right there, fixing X. So let's focus at our head-on view for a minute, because I think it's a little bit easier to imagine what's going on. So we need to figure out what this green area is. Well, notice you got these two concentric circles, this blue circle and this red circle here. We're interested in getting this green area. Well, this is the center of both of them, this little purple dot right here, so I'm going to put that on. And let's look at the two different radii that are kind of involved. So the radius of the blue circle, I'm just going to go ahead and mark that. And I usually denote that by a lowercase r. So that's a small r because it's the smaller radius. Now, there's also the radius of the big red circle. It also is from the center, this blue dot right here, but it's going to go out like this, and I usually label that capital R. Alright, so let's go ahead and figure out what the area of this washer is, what this green area is. So the area of our washer is going to be equal to the entire red circle's area. But that's too much, that's including everything. The entire red circle is all of this. So we need to take away this whole. Right? So we need to actually subtract off the area of the blue circle. Well, what is the area of the red circle? Well, the area of any circle is pi times its radius squared. Well, the area of the red circle is capital R, big R. So let's just go ahead and replace that with pi big R squared. And similarly, the area of the blue circle, again, is just pi times its radius squared, which is pi little r squared. Well, what most people do is rather than leaving it like this, which is still correct, but they both have a pi in common, so let's just go ahead and factor out that pi. So it's just pi times big radius squared minus small radius squared. Well, now that we know the area of this green part, the area of this washer, thinking of our original solid, this big volume right here, is just adding up all these different washers. So the general formula for the area for a solid of revolution is going to be, the volume is the integral starting at A and going to B of pi times big radius squared minus small radius squared. And keep in mind, the big radius and small radius are theoretically changing for all these different slices of x. So x is our main variable. This is all dx. We were chopping up the x there. And just maybe one other little simplification is pi is a constant here in this. So sometimes people just pull that outside the integral like that. Alright, so what we wrote down here is the general formula for the volume of the solid of revolution. Sometimes this is called the washer method. But let's see what it is in our particular case. So here we had the center of our washer, this purple dot right here. Well, what does that correspond to back in our actual solid? Well, that's going to be that spot right there. So, well, what is our big R in this case? So, actually, let's do the little r first. So, this little r over here is going from the purple dot to this blue spot right here. So, going back to our 3D version, there's the purple dot, and there's that blue spot right there. And we know what this length is because we put this dotted line right here, and if you remember, this was the x-axis, and I lowered it by 6. So the length from here to here is always 6, regardless of what slice or x we're at. It doesn't matter whether I take the x here, or here, or here. The blue dot to this blue segment, or blue dot right here, this is always going to be 6 long, because from the dotted line, which is where our purple center is going to be, up to our blue dot, which is always going to be on the x-axis, this length is always 6. Now, that's just this particular problem. I don't want you to think that the big R or the small r is always a constant, but in this particular problem it was. It was always 6. So we can just write that our little r in this problem is always 6. Sometimes it varies depending on where you take the slice. In fact, that's what's going to happen with our big R. So in order to figure out what our big R is in this case, let's focus on this little black segment right over here, which corresponds to this spot in our 3D solid. So if we want to know how long this is, that actually corresponds to the y-coordinate of our red dot right here. Well, how did we get that red dot? Well, this red dot was just on our function f of x. So our big R is just the y-coordinate there. In this case, our f of x was the square root of x. So if this part is the square root of x, how are we going to get the entire big R? Well, the entire big R, you can think of the big R as being measured over here, so it's just 6 plus the square root of x. So that's going to be our big radius. So notice the big radius changes depending where you take your slice. The hole, the blue circle, the actual hole part, that's always staying the same size. But this the red circle is kind of getting bigger and bigger and bigger, so you're getting more and more area as you slide your x this way. Right, well, let's just actually now plug in to our actual equation and figure out the volume of this 3D shape. So we're going to do the integral from 2 to 9, because that's where a and b are. And don't forget, we've got the pi there. And now we've got to look at big R squared, which we know we've figured out that our big radius is the square root of x plus 6, that thing squared. And then we have to take away little r squared. Well, little r in this case is just 6, so just minus 6 squared. And don't forget, we've got a dx out here. Well, I want to go ahead and compute this, but I'm kind of running out of space. So let me see if I can be clever and sort of shrink this off to the side a bit. Haven't done this before. See if this works. Yeah, all right. So this is where we left off. So I'm just going to continue over here and figure out what our volume is. So our volume is the integral from 2 to 9 of, and I'm just going to Pascal triangle out this puppy. It's a perfect square trinomial, so a squared plus 2ab plus b squared. That's how I got this. And then minus 6 squared minus 36. Well, again, I want you to think this always happens, but there's a nice little simplification here, a nice little canceling. So let's just get rid of the 36 minus 36, like so. And at this stage, this is just back to calculus we learned how to do, more than a month ago. So we'll just integrate each piece by piece, term by term, and it's just a power rule, right? So the integral of x is 1/2 x squared. The integral of 12x to the 1/2. Again, you just kind of add 1, 3/2, divide by the new exponent, so it's multiplying by 2/3. 12 times 2/3 is 8. And don't forget, we've got our stick notation. We're going to stick in the values between 2 and 9. So this just means we're going to first plug in 9, subtract what we get when we plug in 2. And again, I'm running out of room a little bit, so I'm going to come up here, and they're sticking in 9, and they're sticking in 2, and really you would just go ahead and do this on the calculator. But if we want an exact answer, you can go ahead and, oh yeah, don't forget, common mistake is to forget to put the pi there, so there was a pi in front of all of that. So we could just do this in the calculator, but I'm going to simplify it first, because if they ask for an exact answer, you just make a common denominator, etc. So the exact answer is 729 minus 48 over root 2 over 3 pi. And if they ask for an approximate answer, you can just go to your calculator and answer with the decimal. So it turns out I go to my calculator, I get 692.321 cubic units. So it could have been this is some sort of word problem and there's units in this. So instead of just arbitrary, 2 and 9, maybe we're talking about feet or something, in which case this would be cubic feet. I just wrote cubic units here. Also, I rounded to 3 decimal places, not exactly 0.321, but on the AP exam, if they ask for an approximation, you can just give to 3 decimal places. So that would be our volume. Here's the exact volume, and this is the approximate volume with decimal points and even 3 units on there. So that is how you find a volume of a solid of revolution. Oh, one last thing I should probably mention before taking off is that I sort of made this problem extra tricky by having the line that it was revolving around be separate from the x-axis. That created this air gap here, but typically that's actually not the case. So generally you see something more like this, where I'm revolving directly around the x-axis. So you're taking your area and you're spinning it around. Now, theoretically, the same formula for volume still applies. It's still, pi times the integral from a to b of big radius squared minus small radius squared dx. But if you think about it in this case, the small radius, the air gap doesn't exist, right? So really your small r is just 0, right? There is no inner circle. There is no inner blue circle anymore. It's all just that one big red circle. So people typically just kind of, in that kind of case, you don't need that little r squared. And if you think about what big R is going to be this time, so big R is just your function value right there. So generally what people are going to do is rewrite this equation in a simpler form. Sometimes people just call this disks instead of washers because you're just adding up all the circles, and they just write it as f of x squared dx.